In this video, we're going to compare standard pocketing step-over versus iMachining's controlled step-over. What we've done is we want to focus on machining this ledge right here, and what one pass or one tool path loop around this ledge would give us with both standard pocketing and an iMachining. To show what the stock looks like before this cut, we'll go to our Solid Verify and play this. Here we have just an iMachining roughing toolpath, and then we also have a finishing toolpath to make sure it's the exact geometry. If we show our target, what we can see is we have this center pocket finished, now ready to machine this ledge. We have a standard pocketing toolpath set up here. As we can see, we have our 4 offset passes to machine that ledge. Let's go into the Solid Verify, and we're going to take a look at what happens. We're going to go to a top view, and we're going to also switch on wireframe so we can see how the tool is cutting. Here we have the tool entering into the first corner. So there's a few things we want to show here and measure. We're going to use a screen capture utility called Jing that I like to use. It's going to allow us to draw some errors on this. Now what we have here is we have a few things going on. We have the toolpath, and we have what the tool is doing along this toolpath. We're going to draw an arrow for the cut direction. Here we have the tool moving in this direction. We can change this color to blue if we like. And we're going to label this as cutting direction. Now, when we look at step over, or really what we're looking at is width of cut, we want to measure width of cut based on the cutting direction. So we're going to draw 2 arrows on where the tool is touching at the first point, here, and where it's touching here. We always want to be measuring with the cutting direction. Now what we see here is this width of cut that this tool is actually taking in the corner, we can see is actually 3 to 4 times larger than the width of cut on straight lines. Generally, when we think of step over or width of cut, we are generally thinking in terms of straight lines. But what happens when you look at the tool changing direction, turning corners, going into concave areas, the direction of the tool is changing, and it's not just cutting a straight line. So what we have here is we have this step over that's increased 4 times over the straight line cut. This is why we get the eek sound in the corner, and also why we notice that the tool gets red hot and we get steam in those corners, because the heat generated is way larger in this corner now because we're taking quadruple the depth of cut, or width of cut. So let's keep on going a little further. Now we have our next motion. Here we did a circle coming around into this little corner. We're going to do the same thing with Jing, and we want to measure what the cutting direction is and what our width of cut is. Now since we're doing a corner, the end result is the cutting direction is generally looking something about like this at the end of the corner. So now if we measure our width of cut, once again going parallel with our cut direction, here we can see the width of cut versus our straight line is something maybe 6-7 times the width of this. So here is where we have all of this tool overloading with standard parallel style toolpaths with our standard step over. As we'll just play through the rest of the toolpath to show you what you get. Now visually what we see is we have a constant width of cut just looking at this visually with our eye. But in reality, as we just saw, the cutting direction is not a straight line, so the width of cut that the tool or the material that the tool is actually removing is not constant by any means. So now let's go take a look and see what iMachining gives us here. We're going to take that pocketing toolpath and just drag it below it. We're going to go back to our Solid Verify. We're going to repeat the exact same steps. We'll zoom in on this corner, we set it to our top view, and we also go to wireframe. And we're going to single step through iMachining. Now the first thing we see here is that iMachining is gently entering into the material. Once we hit here, we can see we're now at our width of cut, or the controlled step over we have. We can see as we're coming into this corner now, we can see that iMachining is starting to roll the tool in this direction, and we can see our width of cut changing. Now, let's use Jing again and let's see what happens here. We're going to draw our arrows again. So what we see is, since we're kind of turning this corner, we basically have the tool coming at a direction roughly like this. Once again, we'll label this cutting direction. We're going to draw our arrows. Now what we can see here is now this width of cut, based on cutting direction, is now the same as the straight line width of cut. Which brings us to our definition of controlled step over. And we'll type this out, that way it's very clear for everybody. So controlled step over is, it is to constantly adjust step over to give a constant width of cut based on cutting direction. So this is important, very important to think of. We all know what step over is, but generally we are only thinking of step over in straight lines. iMachining is using controlled step over. This is where we're actually adjusting the step over to give a constant width of cut. We're going to continue playing through this a little bit. Here we see an interesting thing that happens here. iMachining, as it was trying to cut this corner, there was no way for it to hold the width of cut or the step over that we defined, so the tool actually had to back away and could not get into this corner, for it was impossible to give the user the controlled step over it wanted based on entering into this corner. And then what we'll do is we'll play through one loop. So there we have one loop. Now here we see the very big difference to the standard parallel offset toolpath. Now looking at this, it appears as if we'd have a varying width of cut or a varying step over, because we see different amount of material being removed. But in reality, when we measure the width of cut based on tool direction to give a constant load on the end mill, because we're mostly concerned about what the end mill is doing when it's removing material, not what the toolpath looks like in a CAM software. Here we see we get this varying step over along this entire part. You can see it getting to the thickest points when it's at the straight lines. And what we can do is we'll actually switch to an isometric and just finish playing out this toolpath so we can see iMachining finish. And what iMachining does is it continues to progressively shave away the material in a constant spiral motion with our morphing spirals. Then at the end it goes through and it cleans out all the corners to remove that material. We'll also take a quick look at the toolpath again. So here we have our standard pocketing step over, and here we have our iMachining toolpath, where we can see it's actually varying. Now what we want to do is we want to review what this actually does for us. And once again we're going to use Jing. So what are the effects of not using controlled step over in your CAM software? The easiest thing to look at is the tool load is increased in the corners, i.e. non-straight line cuts. What this is going to lead to is it's going to lead to tool wear and fatigue. It's going to lead to broken tools. It's going to lead to multiple depth of cuts. And when we pick multiple depth of cuts, what this is going to do is it's going to wear the lower portion of the tool's flute. So for instance, if we had a tool with a 1-inch flute length, generally we might only be cutting with a depth of cut of 1/100th thou. So what this means is we had 1-inch flute length, but we only cut with 100 thousandths. That means we never get to use the other 900 thousandths worth of flute length. This is what leads to premature tool wear before the tool's actually finished machining. And I think a lot of us are familiar with retipping end mills, where we grind off the bottom of the end mill and then retip it, because the upper portion of the flute is generally still good. Now the end result is this leads to 1. Slower cycle times, higher quoting costs from that. We have increased tool costs. We have scrap parts from broken tools. And we also have a decreased chance of machining an acceptable first run